Okay, this is lesson 1 of the rates of reaction topic, where we're just going to talk about what is rate of reaction, how to calculate rate of reaction, and importantly how to measure rate of reaction. So the first thing we need to deal with is the actual definition for rate of reaction. Now this is something that is very easy to get wrong, because it's very easy for you to just jump in with the first thing you think of, what is the rate of reaction, how quick a reaction is, or the speed of the reaction, but that doesn't give enough detail. So there are two acceptable definitions for this. It is the amount of product or products produced over time, or the amount of reactants used up over time. Okay, so always over time. Everything in rate of reaction is measured per unit time. So you can either look at it, all chemical reactions have reactants that become products. So over time the reactants are used up and products are produced. So you can either measure the products being produced over time or the reactants being used up over time. Those are the two choices. So how do you measure the products being produced over time, or how do you measure the reactants being used up over time? Well, there's a variety of different things that we can use. Some reactions will decrease in mass. For example, if one of their products was a gas, the gas would be lost to the atmosphere, so the reaction would lose mass over time, and we could measure that. So we could measure decrease in mass over time. In some reactions, one of the reactants is a gas, which is coming from the atmosphere, which is actually going to increase the mass of our reaction mixture. So we might, in some cases, have an increase in mass over time, and we can measure that as well. So increase in mass over time. Going back to the first one where we said we had a gas product, a gas being produced, well, if we could collect that gas and measure its volume, we could measure that over time. So volume of gas. Again, over time. Some reactions, there's no obvious change in mass and there's no gas being produced, but some reactions change colour, and we can measure that. How long does it take for the reaction to change colour? So we can measure that as rate of reaction, so change in colour over time. And also perhaps another example would be a neutralization reaction. Well, if I had a neutralization reaction, I would expect to see a change in pH, which I could measure, and if I measured that over time, again I can get the rate of reaction. So you can't always use these. You can't always measure pH. If it's not a neutralization reaction, then pH won't change and that won't work. You can't always measure volume of gas being produced, because sometimes a gas isn't being produced. You can't always measure the colour change over time, because some reactions don't change colour. So it's all about identifying which of these is suitable depending on the reaction you're looking at. So let's look at a reaction. So here we have calcium carbonate, hydrochloric acid forming calcium chloride, water and carbon dioxide. So the first things we should note is that this is a solid, hydrochloric acid is aqueous, calcium chloride is aqueous, water is a liquid, and the carbon dioxide is a gas. Now from this we don't know that there's going to be any colour change unless you happen to know the colours of all of these substances, which you're not expected to. Okay, what I would focus on immediately is the fact that you have a gas product. So that jumps out to me as telling me, right, there's a gas product, which means that's going to be lost to the atmosphere, which means that my reaction mixture is going to decrease in mass. So I could measure that over time. So this first option here, decrease in mass over time. The second thing that stands out is, again, because I have this gas product, well, what if I was able to collect it and measure the volume of that gas? Well, then I could measure the volume of gas over time, and again, I could determine the rate of reaction that way. Either one would work and give you the exact same answer. It's just about looking at the reaction and identifying what is going to be the easiest thing to measure over time. So we'll start with method 1, the decrease in mass over time. So how would you actually do that? Well, what you would need is a balance. You'd have to have a beaker or something like that with your reaction in it. So my hydrochloric acid and my calcium carbonate. And what would happen is the carbon dioxide would be produced and lost to the surroundings. So what would happen is I would measure the mass of my reaction and it will decrease, but importantly, over time. So I'm also going to need a timer. And this would work. It's as simple as that. Set up your reaction on a balance, measure its mass every 10 seconds for 5 minutes, and you will be able to calculate from that the rate of reaction. So the other thing we were talking about was potentially collecting and measuring the volume of this gas. So a very similar setup. It's the exact same reaction after all. So we're going to measure the volume of gas over time. So the only difference here, we can't use a beaker this time, because if we use a beaker, the gas just escapes and we can't collect it. So we need something that we're able to put a bung into the top and a delivery tube. So you need something with a narrow opening, a narrow neck. So we're thinking things like test tube, boiling tube, conical flask. So if we have a conical flask, again with our reaction in it, hydrochloric acid, calcium carbonate, but because it's got a narrow neck, we're able to put a bung in the top, and then we could just simply have a delivery tube going to a gas syringe. And that will just allow us to measure the volume of gas being produced, because as the gas is produced, it goes through this delivery tube and it moves the plunger in our gas syringe, and then we can measure the volume of gas being produced. And again, we would do that over time using a timer. Now, a slightly more low-tech version of this. Again, the starting point is exactly the same. We're going to need something with a narrow neck that we can put a bung in it. So I'm going to go with the conical flask. Put a bung in the top. Now, instead of a gas syringe, we could just simply use a trough of water with an upside down measuring cylinder. And if you fill that measuring cylinder with water and stick it in to that trough of water, what will happen is, as the gas is being produced from our reaction, it will travel through our delivery tube, it will go into our measuring cylinder, and it will displace the water, and then you can simply use the measurements on the measuring cylinder to measure the volume of gas. And again, importantly, we're going to do this over time, because its rate of reaction is always products produced over time or reactants used up over time. So any one of these methods would allow you to collect enough data to work out the rate of this reaction. Now, another big part of this topic is going to be using math skills, and especially graph skills. Skills that you probably, you're well aware of in maths, but they don't translate so well over to the sciences. So, plotting a graph is pretty much always worth 3 marks, sometimes 4, and they should be the easiest marks in the paper. Okay, so if it's worth 4 marks, then they probably want you to draw the axes as well. Okay, if they don't want you to draw the axes, then it's probably worth 3 marks. So rule of thumb is there will always be 2 marks for plotting all of the data correctly. So make sure you do that in pencil, make sure you double check it, make sure you haven't made any silly mistakes, because every time I'm marking these, I'm always finding there's always one plot that's in the wrong place, and it's just because you've misread the axes. So double check it. It's worth it because they're easy marks. And do it in pencil, because if you mess it up, you can rub it out. So there's usually 2 marks for the plots, 1 mark for the line of best fit. Again, do that in pencil, and it should be a smooth, single, continuous line. So we've not been given any axes here. So whenever you're given a table of data here, if they haven't told you which axis to plot things on, rule of thumb is the first column is your x-axis and your second column is your y-axis, unless you've got repeats of the same experiment and then an average, in which case the average will be your y-axis. And we can identify this because the first column here is always our independent variable, what we're changing. And what we're changing is the time. And the y-axis is going to be what we're measuring, our dependent variable, which is the mass in grams. So independent, always the x-axis, and your dependent is always your y-axis. So let's plot this quickly. So on the x-axis, we want to get up to 120. I'm not going to be able to go up in tens, so I'm going to go up in 20s. So I'm going to start here. So 20, 60. Okay, and again on my y-axis I need to get up to 4. I'm not going to be able to go up in halves, so I'm just going to go up in whole numbers. 1, 2, 3, 4. I'm just going to go slightly beyond what I need on both axes. So the rule of thumb here, if you are given graph paper and asked to draw a graph on it and they haven't given you the axis, you need to use up at least 3/4 of the page. Okay, so if I'd done it much smaller than this, I wouldn't have got away with it. At least 3/4 needs to be taken up. So we're going to start with our plots then. So the first one, 0, 0. The second one, 20 seconds, 1.6 grams. So 20 seconds, 1.6. 40 seconds, 2.6. 60 seconds, 2.9. 80 seconds, 3.7. 100 seconds, 4. 120 seconds, 4. So what we now need is a smooth, continuous line of best fit. Now the first thing I would say, your line of best fit does not need to go through every single point. So it doesn't matter if it misses 1 or 2. Secondly, it doesn't always have to be a straight line. It can be a curve. But if it is a curve, it can only curve in one direction. You can't have it changing direction. So what's common here is for people to start curving, and then they turn this way to get that point, and then they turn back. If it's a curve, it's curving in one continuous direction. It's never dot to dot, and you shouldn't ever sketch it like this, because you just end up with a scruffy line. It needs to be a smooth, continuous line that, to the best of your ability, follows the pattern of the data. So what I would identify straight away is that perhaps this one here doesn't quite fit the trend. It's an anomaly, so I'm going to ignore it. So I'm starting here, and I want a nice smooth line, and I'm just going to double check this actually, make sure I've put it in the right place. So at 60 it's 2.9. Okay, so I haven't made a mistake. I mean, the fact that that wasn't lined up is usually an indicator that it's either an anomaly or you've made a mistake, but I've just double checked it, it is an anomaly. So you've got a nice smooth curve, and you're just going to practice it a couple of times, just like you practice your golf swing, and then you're just going to commit to it. Nice smooth line. Okay, now notice that does not go through every point. It's not perfect, it's actually slightly too low, but it's fine. You will get the marks for that. If you do a sort of sketched one, it won't. If you do dot to dot, you won't. So a nice smooth continuous line. So calculate the mean rate of reaction. So this is a bit like when you run a marathon, for example, and you want to know what your average pace was. What was your average pace for the marathon? You need two bits of information for that. You need to know, number one, how far did you run? Number two, how quickly did you run it? And you stop measuring both of those things at the end, at the finish line. So we need to look at our data, because again, a very common mistake is people think, right, the last reading must be the end, but it isn't. The end is when the reaction stopped, and you can see that actually it didn't stop at 120 seconds, it stopped after 100 seconds. This is the end of the reaction, because it stopped changing after that point. We could have kept measuring it for another 10 minutes. It wouldn't have changed the mass, because the reaction had already finished. So when you're working out the average rate or the mean rate, if you're using data from the table, you just look for when it stops changing. And now, just like in a marathon, where you want to know how far you ran and how long it took, well, how much did it change? Well, it changed by 4 grams, and it took 100 seconds. So the average rate of reaction is 0.04 grams per second. We can do that from the graph as well. All you have to do is look at the graph and find, well, when did it stop changing? Well, here, there's our end point. There's our start point. If you draw a straight line between those 2 points, and then work out the gradient of that line using rise over run. So gradient is equal to the change in the y-axis over the change in the x-axis, or rise over run. So the y-axis has increased from 0 to 4, and it took 100 seconds, 0.04 grams per second. And again, two different methods got us the exact same answer for the average rate. So the other thing they're going to ask you, and again, think about running a marathon. Are you going to run that same pace the whole time? Surely not. You're going to start off quicker and you're going to slow down. I mean, look at our trend line. You can see very clearly the rate is not constant. Okay, when we plot something against time, the gradient is equal to the rate. Okay, so I'm just going to write that up here. So the gradient of the line is equal to the rate of reaction. So the rate of reaction is not constant, and we can see it's not constant because it's curved. If it was a straight line, it would be constant. So the whole time it's steeper, it's going faster, and then when it gets shallower, it's going slower, and then when it levels off, it's stopped completely. So it starts off quickly and it slows down. So yes, the average rate of reaction was 0.04 grams per second, but was that the rate of reaction at 20 seconds? No, it was faster at 20 seconds. Is that the rate of reaction at 80 seconds? No, it was actually slower at 80 seconds. So how can we go about calculating the rate of reaction at a given moment in time? And the way we do that is by taking a tangent. Okay, so it says use the information on the next page to help you. Now, if you do turn the page, I've got some tutorials here that talk you through, just like I have, how to calculate the average rate of reaction, but also how to calculate the rate of reaction at a particular time. So this one's for the example of 40 seconds, by drawing a tangent and then working out the gradient of that tangent. And that will allow you to work out the rate of reaction at any given moment. And that's called the instantaneous rate. So I'm going to show you quickly on here. So it says here, use your graph to calculate the instantaneous rate of reaction at the following times: 20 seconds, 50 seconds, 80 seconds. So we'll start with 20 seconds. The first thing we need to do is go find 20 seconds and go up to our trend line. Okay, then we're going to take our ruler, and where that intersected our trend line, we're going to place our pencil, and we're going to put our ruler onto our pencil, and we're going to draw a tangent. And what you want from your tangent is, number one, it shouldn't cut through. So if I did that, that's no good. That's going to cut through my trend line, so it shouldn't do that. And you want it to sort of pivot on your pencil, and you want to, as best you can, make the angle here the same as the angle here. And then we're just going to draw our tangent there. So now we've got our tangent, we need to work out the gradient of that line, of that tangent. So we're going to do that by turning it into a right-angled triangle. So I'm just going to go across here. So how much has it gone across by? It's gone across by 64. If each one of these is 2, 62, 64, yeah, so that's gone across by 64. How much has it gone up by? Well, it starts at 0.3, it goes up to 4, so 3.7. So again, so for this one, let's just show changing the y-axis over the change in the x-axis. So the y-axis has gone up by 3.7. The x-axis has increased by 64. So 3.7 divided by 64 is 0.058 grams per second. And as you can see, that is faster than the average, which is what we'd expect because it's steeper here. At the beginning it would be faster, of course it would be faster. I'm going to skip straight to 80 seconds now. I'm not going to bother with 50 seconds. I'm going to go straight to 80 seconds. Same method. I'm going to go from 80. I'm going to extrapolate up to my line of best fit. And from that point, I'm going to draw another tangent. Again, trying to keep the angle here and the angle here the same. So I'm going to have to tilt it about that way. Okay, there you go. There's my new tangent. So again, we're going to turn that into a right angle triangle, and I'm going to do that here, just because that's on a whole number, makes life a bit easier. So how much has the, oh, I'm going to have to extend this now, sorry, that was my mistake, so that's going to have to be 160. So this has, so 140, 142, 144, 146, 148, 150, 152, 154. And how much has the y-axis increased by? So it's gone from 2.1 to 5, so 2.9. So change in y over change in x. So the y-axis increased by 2.9. The x-axis increased by 154. Again, that was 2.9 grams, 154 seconds. So 2.9 over 154 equals 0.019 grams per second. And you can see that is slower than the average, which is again exactly what we'd expect, because it's steeper here, it's faster than the average, but it has slowed down here where it's shallower than the average. So it starts off fast and ends slow. And we can see that by looking at the rate of reaction at those particular moments. And I skipped the 50 seconds just because the graph is already pretty busy. I don't want to complicate it. So if you want to work out the average rate, then you can just use the table of data if you've got it, find when it stops, and then divide the whatever you've measured by the amount of time taken. So here it was mass lost divided by time taken, but that might have been volume of gas produced by time taken. It would change the units. The units depend on what you're measuring. It's always going to be per second, but it depends what you're measuring. Here we measured grams because we were measuring mass lost. If we were measuring volume of gas over time, then this wouldn't be grams per second, it would be centimeters cubed per second. So the units are always going to be per second, but it might not always be grams, it might be centimeter cubed. It just depends what you've been measuring. If you want to know the rate of reaction at any given moment, any particular time, then you have to use your line of best fit, draw a tangent at that point, and then calculate the gradient of that tangent. Again, using rise over run. Again, there's something you do in maths all the time, and you'll be able to get the rate of reaction at any given moment. So again, you're able to re-watch this video as many times as you want. You know, if this made sense while I was explaining it and then you're trying to do it later and it doesn't make sense, you can always refer back to this video, but also look at this page in your pack, which again explains it. And again, just follow these steps and it will work every time. So the final thing I want to talk about is describe and explain the pattern you observe, and make sure you refer to collision theory. Now, before we do that, it would help if you knew what collision theory was. So, collision theory basically means that in order to react, and become products, reactants must 1. Collide, 2. Have enough energy to react, and we call that the activation energy, which we've already come across when we're doing our reaction profile diagrams. So this is collision theory. In order to react and become products, reactants must first collide with each other, and secondly have enough energy to react. So whenever we're talking about rate of reaction and things that increase or decrease rate of reaction, this is what we're talking about. We're talking about collision theory. So let's apply that here. So describe and explain the pattern you observe. So describe and explain. This bit is easy. Just look at the graph and describe what's happening. So as I go along the x-axis, time is increasing. What happens to the mass lost? Well, that increases. So, mass lost increases over time. That's a nice easy mark just there. Mass loss increases over time because as I'm going across the x-axis, my values on the y-axis are increasing. So the mass lost is increasing over time. If this had been going down, we could say it decreases over time. The second thing we can identify is it happening at a constant rate? Well, no, because this is not a straight line, it's a curve. So it's slowing down. You can tell by the steepness of this curve. Okay, where it's steep, it's going fast, and where it's shallow, it's going slow. So it's slowing down over time. So that's our second mark. Rate of reaction slows over time. And then finally, we can say that after 100 seconds, the reaction has finished. So that's just the describe and explain. So let's talk about collision theory. So why does that happen? Why does the rate slow down? Why does the reaction finish? So if I just very quickly sketch you a graph, let's make up a reaction. Let's say A plus B makes C. So here is my graph. Here I've got concentration, and here I've got time. So at the very beginning of the reaction, I've got quite a lot of A, I've got quite a lot of B, and I've got absolutely no C. No products have been produced yet. So over time, A and B are going to react and start producing C. So C is going to increase, isn't it? It's a product. It's going to increase over time. A and B are going to react and they're going to get used up over time. So what we can see is our reactants are being used up over time and our product is being produced over time. So this is clearly our product and these are clearly our reactants. Now what we can say is the rate of reaction slows down, and you can see that by the curve. It's nice and steep at the beginning, going fast, and then it's nice and shallow here where it's going slow. And you could also see, if I go down there, is the reaction stops. Now the reason why it stopped is because reactant B has run out. And as soon as one of your reactants runs out, that is it, game over, that's the end of your reaction. So the reason why it stopped is because B ran out. So a reaction stops the second a reactant runs out. But why does it slow down? Well, let's go back to collision theory. They have to collide and have enough energy to react. So we're not talking about the energy, but we are talking about the collisions. In the beginning of the reaction, there's lots of A and lots of B. There's quite a large chance of them colliding with each other. But as they're being used up, and there's now less A and there's less B, the chances of them colliding is going to be less. So the rate of reaction is going to be less. And that's precisely what happens here. We can see it starts off steep because the concentration of calcium carbonate and hydrochloric acid is high. So the chances of them bumping into each other and reacting is high. So the rate of reaction is high. But as they're getting used up, there's going to be less and less particles of hydrochloric acid and calcium carbonate. The chances of them colliding becomes less and less, so the rate of reaction becomes less and less. And at 100 seconds, what happens? Well, one of them runs out. So that's what we need to say. So at the beginning, there is a high concentration of reactants. Therefore, greater frequency of collisions. As reactants get used up, the frequency of collisions becomes less. And because the frequency of the collisions is less, the rate of reaction is less. And finally, the reaction stops when one reactant runs out. Okay, so just from that graph there, we can identify all of this information. We can see clearly that the mass lost is increasing over time. The rate of reaction is slowing down over time because we can see it's a curve and it's getting shallower. If it was doing the opposite, if it was getting steeper and curving this way, we'd say it was getting faster over time. After 100 seconds, the reaction is finished, and you can see that because it stops changing after 100 seconds. And the reason why, because at the beginning there's a very high concentration of reactants, so there's a greater frequency of collisions. And as the reactants get used up, the frequency of collisions becomes less because their concentration is less. And finally, the reaction will stop as soon as any one reactant runs out. And as per usual, there's some exam questions for you to complete, and there'll be a mark scheme coming out at a later date.